Let's discuss about a simple pendulum. A simple pendulum consists of a heavy point mass suspended above the point of suspension by a long, inextensible and flexible string or thread. Now, a simple pendulum cannot be achieved in practice because we are not having a point mass, but the nearness can be achieved by taking a small metallic sphere, small heavy metallic sphere, and a thread of unspun cotton that needs to be suspended above the point of suspension like this. When this mass is given some angular displacement, that is theta, we know that the weight of bob is directly downwards, that is mg. This mg can be resolved into two components, vertical and horizontal component. This horizontal component is mg cos theta and this vertical component is mg sin theta. As seen, the horizontal component mg cos theta is opposite to the tension in the string if it is taut. So mg cos theta is equal to T. Now this mg sin theta brings or tries to bring this bob back to the mean position. At this mean position, this extreme position, this mg sin theta restores the bob to its mean position. But here we are dealing with the angular displacements, so here we are going to take restoring torques. Now here the restoring torque is equal to minus mg sin theta into L. Mg sin theta into L. As these are perpendicular, we know that mg sin theta into L is equal to restoring torque. For small angular displacements in the radians, listen closely. For smaller angular displacement in radians that are less than 10 degrees, sin theta can be replaced by theta. So torque is equal to minus mg into theta into L. Torque is equal to minus mgl into theta. Taking it as mgl as spring factor, go torque is equal to minus k theta, where k spring factor, k is equal to mg into L. Now the time period, as already calculated in the previous lectures, time period is equal to 2 pi root of inertia factor by spring factor. So T is equal to 2 pi root of. Here inertia factor will be the moment of inertia of this mass about this length L, and that is equal to ml square. So it is equal to ml square divided by spring factor is equal to k, that is equal to mgl. So m and m goes, 1 L and L goes. So time period of simple pendulum is equal to 2 pi root of L divided by G. Now this L is the length, the effective length of the simple pendulum, and G is the acceleration due to gravity at that point. So from the equation it is clear that the time period of a simple pendulum doesn't depend upon the mass of the bob. It depends upon the gravitational acceleration, that is G, and L, the effective length of the simple pendulum. Talking of the different cases, as we know that time period is 2 pi root of L divided by G. So if we take a pendulum clock, remember a pendulum clock on the hills or inside the mines, we know that with the height the value of the G decreases, and with the depth inside the earth the value of the G decreases. So when we take a pendulum clock on the hills or inside the mines, as the value of the G decreases, so T increases. If T increases, that means the clock loses time. The clock loses time. It's number one. And number two. Number two is, if we are having a pendulum clock on a track that is going up the incline, that is going up the incline of the inclination theta, the effective G here will be equal to G cos of theta, as the effective g will be g cos of theta. So time period of simple pendulum in that track is equal to 2 pi root of L divided by g cos of theta. Case number 3, a second pendulum. A second pendulum is a pendulum that beats seconds. That means that has a time period of 2 seconds. What is the length of that pendulum? Let us calculate. So t is equal to 2 seconds is equal to 2 pi root of L divided by g. Now that is equal to 4 by 4 pi square into 9.8, that is equal to L. When we calculate the L, that equals to 0.993 meters, or L is equal to 99.3 centimeters. So the length of the second pendulum is 99.3 centimeters. Taking the case of the pendulums in elevators, we have got 3 cases. Now, if the elevator is going upwards with an acceleration a, if the elevator is going downwards with the acceleration g, if the elevator is falling freely. In case number 1, the effective acceleration due to gravity is g plus a. The effective acceleration of the gravity in second case will be equal to g minus a, and the effective acceleration due to gravity will be 0, that is, it is falling freely. In first case, the time period will be equal to 2 pi root of L divided by g plus a, and in the second case that will be equal to 2 pi root of L by g minus a, and in the third case, when the elevator is falling freely, that will be equal to 2 pi root of L divided by 0, that is equal to infinity. That means if a pendulum clock is in an elevator that is falling freely, or in a container that is falling freely, as the effective acceleration due to gravity is equal to 0, that means the time period of that simple pendulum is equal to infinity. That means the pendulum doesn't oscillate. Last case, if the carriage is moving with an acceleration a in the horizontal direction, that means the effective acceleration due to gravity is equal to root of g square plus a square. Now we know that this g and a are perpendicular, so their resultant should be equal to root of g square plus a square. That is equal to g dash is equal to root of g square plus a square. The time period of the simple pendulum in this type of carriage is equal to t is equal to 2 pi root of L divided by g dash, and that is equal to 2 pi root of L divided by g square plus a square root